This is the second video in the self-study unit on Lewis structures and shapes of molecules, and this is about the shapes of simple molecules. And so we're going to start out first off by talking about the idea of what we call ABX. And so if you go back to the discussion we were having in the video on drawing Lewis structures, it was generally the case that we had some central atom surrounded by two or more flanking atoms that were of the same element. So you had element A in the middle, and then say 2, 3, or 4 of element B surrounding it in your Lewis structure. And so the idea of ABX is simply that A is that central atom, B are the surrounding atoms, which tend to be of the same as each other, but different element than A. And then X would be the number of B atoms in the formula. And so I've given some examples here of various ABXs. Under AB4, you can see there's CH4, CCl4, SF4. Again, one central atom and 4 surrounding atoms. Examples of AB3 would be ammonia, NH3, boron trifluoride, and chlorine trifluoride. And then examples of AB2 would be water, carbon dioxide, and sulfur dioxide. And so then the question arises, well, does the ABX designation of a particular substance determine its shape? And the answer, if you look at these models I've got shown here, you should quickly realize the answer is no, because you can see that I've got 3 different AB3s here. I've got ammonia, I've got boron trifluoride, and I've got chlorine trifluoride. And you can see that each of them has a different shape. This one is ammonia is what's called trigonal pyramidal, and so the 3 hydrogen atoms are in the same plane, but the nitrogen atom is not in that plane. By contrast, in BF3, all 4 atoms are in the same plane. And then you have this odd T-shaped looking molecule here for chlorine trifluoride. So the upshot of this is that the ABX designation does not necessarily tell you what the shape is. Similarly here, for some examples of AB2, water is a bent molecule, whereas carbon dioxide is linear. So there are multiple possible shapes for each given ABX category. So what is it actually that's determining the shape? Well, in order to figure out the shape of a molecule, it's not enough to simply know the formula and therefore it's sort of ABX designation. You have to have a Lewis structure, because the shape of a molecule is actually determined not by the number of flanking atoms, but by the number of flanking atoms and non-bonding electron domains around the central atom. So if you see here, in each of these AB3s, there are 3 flanking atoms around the central atom. But the difference between them is that in this molecule, boron has no non-bonding pairs. In ammonia, nitrogen has 1 non-bonding pair. And then in the chlorine trifluoride, the chlorine has 2 non-bonding pairs. And so it's the actual number of electron domains, both bonding and non-bonding, around the central atom that determines the shape. So this is all based on what we call VSEPR theory, and although it's pronounced Vesper, it's actually not spelled Vesper, it's VSEPR, and that stands for valence shell electron pair repulsion. And the simplest statement of this that I've found to put on here is this: the most stable arrangement of electrons in a molecule is one that keeps electron pairs as far away from each other as possible. And so you can think about this with balloons. If you had 2 balloons, and that would represent, say, a linear geometry, because the furthest 2 balloons can get away from each other would be 180 degrees apart. If you had 3 balloons, the furthest they can get away from each other is in a plane with balloon to center to balloon angles of 120 degrees. And if you had 4 balloons, they would adopt this tetrahedral shape, in which all these bond angles are about 110 degrees. But this is now a 3-dimensional shape. These are things that you could actually depict in one plane, but a tetrahedral shape, actually, you can't depict on a piece of paper really accurately, because it's actually a 3-dimensional shape. So again, shape is determined by the number of electron pairs around the central atom. And in boron trifluoride, there are 3 electron pairs around the central atom. In ammonia, there are 4 electron pairs, 3 of which are bonding and 1 of which is non-bonding. In chlorine trifluoride, which is one of the types of molecules that has an expanded octet, there are actually 5 5 electron pairs around the central chlorine atom, 3 of which are bonding and 2 of which are non-bonding. So here are the fundamental geometries, electron geometries. And by the way, this is a presentation that I wrote for my organic chemistry class. And so I'm going to, once I get to the end of these slides, I'm actually going to switch to another presentation that goes into this in a little bit deeper detail. But these are the 3 most common electron geometries, whether we're talking about organic molecules or not. And that is a linear geometry in which you have 2 electron domains, and they're 180 degrees apart. A trigonal planar electron geometry in which there are 3 domains, and they are in one plane, 120 degrees angles. And then the tetrahedral, in which you've got 4 domains, and they occupy a 3-dimensional shape in which these bond angles are ideally 109.5 degrees. Now, we want to clarify what we mean by the term electron domain, because while it often means 2 electrons, it doesn't necessarily have to be 2 electrons. A double bond is also considered 1 domain. So we can refer to electron pairs as electron domains, but a double bond or a triple bond counts as only 1 domain. So for example, if you look at this AB3 molecule, A is making 4 bonds, single bond to B, single bond to B, double bond to B, but we would say that it has 3 domains. There is 1 domain going in this direction that's a single bond, another domain going in that direction that's a single bond, and another domain going in that direction that is a double bond. And so because whether it's a double bond or a triple bond, all the electrons in that double or triple bond, single, double, or triple, are pointing in the same direction, we treat it as a single domain. So here are some examples of, and again, these are from organic chemistry, but they'll do just fine for us. Because, and in organic chemistry, we focus on carbon, but carbon always makes 4 bonds. And you can see that in each of these 3 molecules, this is propene, this is formaldehyde, and this is methane, carbon is making 4 bonds. Here it's making a single and a triple, and so it has 2 domains, a single bond domain in that direction, a triple bond domain in that direction, and this would have a linear geometry because there are only 2 domains on that carbon. This carbon in formaldehyde, again, is making 4 bonds, single, single, double, for a total of 4, but because one of them is a double bond, it only has 3 domains, a single bond domain in this direction, a single bond domain in that direction, a double bond domain in that direction. In methane, CH4, it is making 4 bonds, but now they are all single bonds, and so it has the tetrahedral shape. This, by the way, the use of the wedge, which means that hydrogen is coming sort of towards you out of the screen, and the dash, which means that hydrogen is sort of going back and away from you behind the screen. Whereas these 3 atoms, hydrogen, carbon, and hydrogen, are in the plane of the screen. That is a typical way of trying to depict a tetrahedral atom. Now, suppose you have a tetrahedral electron geometry, which you have here in methane. Does that mean you have a tetrahedral molecule? Well, that depends on how many of those domains are bonding versus non-bonding. So as you see here, there's a tetrahedral electron domain. All of them are bonding domains, and so we have what we call a tetrahedral molecule, and so methane, CH4, would be an example of that. If one of those domains is non-bonding instead of bonding, we remove that atom. Its electron pair remains there because there are still, so for example, NH3, ammonia, has 4 total domains, 3 of which are bonding to hydrogen atoms, and 1 of which is non-bonding and just sits up here. And so it gives us this trigonal pyramidal geometry. And then this would represent water. So water has a what we call a bent geometry. There's still a tetrahedral electron geometry. There's a non-bonding pair going in that direction and a non-bonding pair going in that direction. But the atoms themselves, hydrogen, oxygen, hydrogen, give what's called a bent shape. So for each electron geometry, the possibility exists that there's more than one molecular geometry. And for tetrahedral, we have the possibility of tetrahedral, trigonal pyramidal, or bent. So this is another depiction of the same thing. If I've got a tetrahedral electron geometry with no non-bonding domains, I've got a tetrahedral molecule like methane. If I've got a tetrahedral electron geometry with one non-bonding domain, then I've got a trigonal pyramidal geometry like ammonia. And if I have a tetrahedral domain with two bonding and two non-bonding domains, then I've got a bent molecule like water. I've given some other examples here. This is propane, in which all of the bonds around these three carbon atoms are tetrahedral. Here is trimethylamine, in which this nitrogen in the middle it's a little bit tough to see, but has a trigonal pyramidal shape, in which it is not in the same plane as the three carbon atoms. Here's an oxygen in ethanol, it has a bent shape, and that is again because there are two non-bonding electron domains attached to this oxygen atom. They're just not shown in the model. The worksheet that I posted along with this video that has to do with writing both writing Lewis structures and determining shapes actually has a nice little chart on the back that says for this many total domains, of which this many are bonding and that many are non-bonding, this is the given molecular shape. If you have trigonal pyramidal, trigonal planar electron geometry with no non-bonding domains, for example, BF3, sulfur trioxide, formaldehyde here, then you are going to have a trigonal planar shape. If you have a trigonal planar electron geometry with one non-bonding domain, for example, the nitrite anion that they're showing here, another example would be sulfur dioxide, then you would have what we would call a bent. And that is an interesting thing because there are two bent geometries. There's a bent geometry with the 109-degree geometry of a tetrahedral arrangement, and then there's a bent geometry with the 120-degree angle of a trigonal planar arrangement. This is just another example of a trigonal planar geometry. The benzene molecule has each of these carbons in a benzene molecule is trigonal planar. And finally, you can have linear, and so they're going to be in a linear arrangement, you're going to have two bonding domains and no non-bonding domains, and carbon dioxide is going to be the best example of that. And then, of course, if you just have any molecule that can just diatomic molecule like HCl or H2 or O2, that is by definition going to have a linear geometry because there are only two atoms in it. Okay, that's the end of this presentation, so I'm going to switch over to the other. I'm going to talk briefly now about the effect of non-bonding electrons and double and triple bond electrons on the bond angles in a molecule. For a tetrahedral arrangement, I had mentioned earlier that 109.5 degrees is the angle of all four of these bond angles here. So this HCH, this HCH, this HCH, and this HCH are all 109.5 degrees. A non-bonding pair is larger and occupies more space than a bonding pair, and that's the point that's being made here, that a bonding pair of electrons is localized between the two atoms into a smaller region of space than a non-bonding pair. And what that has the effect of doing is actually squeezing bond angles. And so if I take away a hydrogen and replace it with a non-bonding pair like I have in ammonia, that actually squeezes down these bond angles. This HNH is now 107 degrees, not 109.5, because this non-bonding domain is larger than these other three domains, and it pushes the other three domains closer to each other. And if you get to water, that squeezes it down even more, because now you've got two non-bonding domains that are, again, larger than the bonding domains, and so they are going to press in on these bonding domains and squeeze them closer together. And so the bond angle in water is actually 104.5 degrees, which is 5 degrees smaller than the bond angle in methane. Similarly to that is the fact that a double bond or a triple bond occupies more, the electrons occupy more space than a single bond. And therefore, in a phosgene, which is a trigonal planar molecule, the bond angles are not all 120 degrees. And the reason is because this carbon-oxygen double bond, there's more volume occupied by those electrons than the single bonds. And so these single bonds get squeezed closer together. And so these OCCl bond angles are both larger than 120 degrees, and the ClCCl bond angle is smaller than 120 degrees. You don't need to memorize these bond angle numbers either on this slide or on the previous slide. You just need to be aware of the general fact that a non-bonding pair or a double bond or a triple bond is large, those electrons occupy a larger volume than a single bond, and they are going to squeeze these bond angles down. We've talked mostly about the three electron geometries associated with molecules that obey the octet rule or have fewer than 8 electrons in their valence shell, but there are a couple of electron geometries for central atoms that have expanded octets. If a central atom has 10 electrons in its, or has 10 electrons, and those are 5 different electron domains, then it has what's called a trigonal bipyramidal electron domain. And those bond angles, this is a unique electron geometry because it has actually 2 different sets of bond angles. Because if you look closely at this molecule, there are 2 atoms going straight up and down, which we would call axial, and then there are 3 atoms going around that we would call equatorial. And so the bond atom from axial to central to equatorial is 90 degrees. So that's a 90-degree bond, that's a 90-degree bond, this is a 90-degree bond, etc. But then the bonds along the equator are 120 degrees. So that bond from atom there to center to that atom there is 120 degrees. That bond from that atom there to central to that atom there is 120 degrees. If you replace one of those bonding domains with a non-bonding domain, you get what's called a seesaw shape. So this would be total of 5 domains, of which 4 are bonding and 1 is non-bonding. That's called a seesaw. And then, and as it turns out, anytime you remove a bonding atom from a trigonal bipyramidal shape, you take it from a equatorial position. So you can see that the 2 axial positions are still intact, and you have 2 atoms left along the equator. That is called a seesaw. If you make 2 of them non-bonding, now you get what's called a T-shape. And if you go way back to the beginning of this presentation, when I showed you chlorine trifluoride, that was a T-shaped molecule. And then if you have 5 domains of which only 2 are bonding and 3 are non-bonding, then you've removed all the bonding atoms from the equator and you have a linear shape. If you have 12 electrons around the central atom and they comprise 6 total domains, that's what's called an octahedral arrangement. In an octahedral arrangement, all of the bond angles are 90 degrees, and there are 3 possibilities for what the molecular geometry could be. If you've got 6 domains and they're all bonding, then you've got an octahedral molecule. If you've got 6 domains of which 5 are bonding and 1 is non-bonding, this is called square pyramidal. And if you have a octahedral arrangement in which 4 are bonding and 2 are non-bonding, that's called square planar. Xenon tetrafluoride is an example of that. I think that was a molecule that I had featured in the video on drawing Lewis structures. Bromine pentafluoride is an example of a square pyramidal molecule, and sulfur hexafluoride is an example of an octahedral molecule. This also applies to molecules that have more than one central atom, which is very much the case in organic chemistry, particularly. And so we can have for example, here is acetic acid. We talk about acetic acid all the time when we're talking about acid-base equilibria, but here is the actual three-dimensional depiction of an acetic acid molecule. And what you can see there is that you consider this has more than one central atom. Here is a carbon atom that is tetrahedral because it's making 4 single bonds, 3 to hydrogen and 1 to carbon. Here's a carbon atom that is trigonal planar because it has 3 domains, 2 single bond domains and a double bond domain. And here's an oxygen atom that is bent because it has 4 domains, 2 bonding domains, 1 to carbon and 1 to hydrogen, and 2 non-bonding domains. So you've got 3 different atoms. You've got 3 different. You've got 3 different atoms. You've got 3 different central atoms. You've got 3 different geometries. Okay, that's the end of the presentation on shape. And so, as I mentioned at the end of the previous video, there is one assignment in the folder that has to do with drawing Lewis structures and with determining their shapes. And then I'm also going to post a worksheet for what's called a PHET simulation on shape, which is a really wonderful thing you can just play with on your computer and add non-bonding electrons and add bonding electrons and add single and double and triple bonds to things and just see what kind of shape arises. And so that I would strongly encourage you to do that simulation activity as well as the other worksheets. All right, enjoy.